Hallå! Varmt välkomna till Scalateatern. Jag heter Martina och jag är förlagschef på Fri Tanke som arrangerar den här kvällen med den anspråkslösa frågan om tidens uppkomst. Ni har ett par timmar framför er med samtal och musik. Vi kommer inte ha någon paus ikväll. Men vi kommer som vanligt ha bokförsäljning efter samtalen och boksignering. Så det är allt lugnt där. Och med det sagt så har jag inte så mycket mer information till er nu, utan jag lämnar scenen till kvällens talare och musiker och önskar er en riktigt trevlig kväll.
So long ago when I was small, all summer long it had a fair, wonderful fair with swings and all. I used to love my little fair, and at the close of every day I could be found dancing around a merry-go-round that used to play. Ah, mon amour, à toi toujours. Dans tes grands yeux, rien que nous deux. All summer long my little fair made every day seem like a holiday. Night after night it used to play. People came there from so far away. I sometimes hear that little tune playing in a dream of long ago. Even Pepe from Napoli, he sang to Marie this serenade. Mon amour, à toi toujours. Dans tes grands yeux, rien que nous deux. I can't forget my little fair, even though I'm so far away. I can't forget my little fair. Maybe it's still there today. I sometimes hear that little tune playing in a dream of long ago, and in my brain runs the refrain, that French refrain I used to know. Mon amour, à Somewhere over the rainbow, way up high, there's a land that I heard of once in a lullaby. Somewhere over the rainbow skies, they are blue, and all of those dreams that you dare to dream really do come true. Someday I wish upon a star and wake up where the clouds are far behind me, where all those troubles melt like lemon drops away above the chimney tops. That's where you'll find me. Somewhere over the rainbow, bluebirds, how they fly. If those birds can fly over the rainbow, why, then oh why can't I? I wish upon a star and wake up where the clouds are far behind me, where troubles melt like lemon drops away above the chimney tops. That's where you'll find me, somewhere over the rainbow. Bluebirds, how they fly. If birds can fly over the rainbow, why then oh why can't I? If happy little bluebirds fly beyond the rainbow, why, oh, why can't I?
Isabella Lundgren, Fri Tankes egen primadonna och backluraband. Varmt välkomna ska ni vara till en kväll om alltings början. Det är inte så ofta man liksom går ut en kväll så här och lyssnar på ett samtal om alltings början. Det brukar handla om liksom att leva i nuet eller ta hand om sig själv eller sådär. Men ikväll ska vi alltså prata om det som hände för 13,8 miljarder år sedan. Det gör man inte varje dag. Christer Sturmark heter jag, vd för vetenskapsförlaget Fri Tanke. Vi ska alltså prata om de kanske djupaste existentiella frågorna som finns. Hur började allt? Varför? Hur började tiden? Och varför finns det överhuvudtaget någonting snarare än ingenting? I will switch to English now as that will be the language for tonight, of course. And it is with great pleasure that I welcome our keynote speaker this evening. As a leading figure in the realm of theoretical physics, he continues to expand the boundaries of our understanding of the cosmos. In collaboration with the late Stephen Hawking at Cambridge, he has made significant strides in the study of the early universe, the Big Bang. His work has reshaped our conceptual framework of the origin of the universe and the very fabric of space-time. So, ladies and gentlemen, please welcome Professor Thomas Hertog.
Hey. Okay, thank you, Christer, and thank you all for coming out tonight. It's a great pleasure to be here in Stockholm. And so, yeah, the story of my book is the story of my collaboration with Hawking and what we found out about the universe. This began 25 years ago. Well, our collaboration, not the universe. When Stephen Hawking invited me to his office to discuss the Big Bang. That was his idea of a job interview. This was his office at the time. And that's also how I found him, smiling, sitting in his wheelchair, and surrounded by the usual stuff that a theoretical physicist need. Lots of books, a dysfunctional desktop, and a picture of Marilyn Monroe on the wall. So Stephen had lost his natural voice at that time, but he could talk through a computer voice. and which he directed with a mouse which was carefully placed in his hand. And this is what he asked me at the time.
The universe appears designed. Why is it the way it is?
So, good luck with your next job interview. Now, what did Stephen mean? In fact, it took me 25 years to figure out what he meant. Of course, this feeling that there's a design behind the world, that there's a grand plan, is familiar from biology, from the living world. And in the old days, we thought that design meant there had to be a designer. Now we know that the apparent design of the living world, the DNA molecule, the eye, the brain, is the result of a gradual evolution. But the design of the universe runs deeper. If you look at these images of the James Webb Telescope, then you see these giant clouds of gas where new stars and planets are formed. Well, in these clouds of gas, we already see the atoms and the organic molecules that at one day can be the chemical building blocks of life. But the universe wasn't born with these clouds of gas. They're the result of 13 billion years of evolution, governed by the laws of physics. And it's at that level, at the level of physics, that you find the most mind-boggling signatures of design. Because it so happens that the laws of physics, the rules on which the universe runs, have a whole number of properties that are seemingly perfect for life, that makes life possible. From the types of forces, the kinds of particles, the composition of the universe, the simple fact that we have 3 dimensions of space. If you change anything in these laws of physics, quickly you end up with a universe that is lifeless, that has no structure, that has no chemistry, that has not the basic conditions for life. And it's at that level, the level of physics, that was the core of the question that Hawking was posing. How is it possible that the laws of physics at some basic level encode the conditions for life? It's almost as if somehow the universe has known all along that one day it would be our home. That was the question that Stephen, frankly, was obsessed with. And why was he obsessed with that question? Later I realized that it was, sure, it's a great question, and by studying it, we're going to learn something about the universe. But I think Stephen felt that we were also going to learn something about our place in the universe, about ourselves. It was fundamentally, for Hawking, I think, a humanist question that he was asking. So yeah, what about the laws of physics? I have to take you onto a journey almost into the origin of the deeper nature of the laws of physics. And you can think of the laws of physics as a barcode. In fact, ever since Newton, since Isaac Newton, we think of the laws of physics as some sort of barcode, mathematical relationships which encode the workings of the universe. And it must be said, these laws that Newton wrote down, they work pretty well, right? We use them today still, and they work fine. In fact, one of the most amazing moments in science in the 19th century was when a French astronomer used Newton's laws to calculate, to predict that there should be a new planet in the solar system. And that planet turned out to be Neptune. So whatever you guys think of the French, I don't know, they did discover a new planet just by calculating, which is quite amazing. And so the whole idea grew since Newton. These laws, they're like a barcode. They transcend the universe. They're mathematical truths up there in their Platonic realm. Albert Einstein, thought about it exactly like that. He was interested in finding the ultimate law, the final theory, that determined how the universe should be. So for people like Newton and Einstein and many other physicists since them, the answer to the question of design was that essentially it's a mathematical necessity. The laws of physics have to be like this. They sort of encode the fact that the universe should be fit for life. But you see, Einstein is looking a little confused. And indeed, things were not going according to plan. In fact, it's Einstein's very own theory that undermined this Platonic idea. And this I want to explain. So what is his theory? This is his theory. Einstein wrote down this amazing equation, an equation which works better than Newton's. It may look complicated, but in fact it's easy to read. There's the left-hand side and the right-hand side, like all equations. On the left, you have the shape of space, and on the right, you have matter and energy, particles, and so forth. And the magic of this equation is, of course, the equal sign in the middle. That says that there's a dialogue between stuff on the one hand and the shape of space on the other hand. And that dialogue, Einstein said, that's what we know and love as gravity. If you take the Earth, the mass of the Earth, according to that equation, will slightly curve, slightly bend space in its neighborhood. And it's that curve, that curvature, that bending, that keeps an object like the moon nicely in orbit around our planet. That was the heart, the core of Einstein's grand new theory. So that's all fine. This works great. But then the problem came from Belgium, in fact. You see, there was this Belgian, Georges Lemaitre. He was a priest and an astronomer. And he decided to push Einstein's equation to its limits. He decided, all right, Einstein, I'm going to take your equation and put all the galaxies, all the matter on the right-hand side. I'm going to apply it to the entire universe, to all of space. And then Lemaitre walked over to the other side, to the shape of space side of the equation, and he found that the universe can't stand still, that the universe must expand. This eternal cosmos idea of Newton is just not there in Einstein's theory. As a consequence, of course, if the universe expands, if space itself expands, then galaxies are moving away from one another. But then if you reverse the order of time, you should get worried, because all these galaxies are on top of each other in the far past. And in fact, this is exactly what Lemaitre did. Lemaitre, with Einstein's equation, turned the arrow of time backwards and concluded that, of course, space itself shrinks, and there is a moment in the past where the very fabric of reality, space and time, cease to be. And that, of course, today we know as the Big Bang. So what do you do when you discover the Big Bang? Lemaitre was a priest, so he couldn't tell his wife. He also couldn't quite tell the Pope. But, of course, he had to tell Einstein, and he did. The two chaps met up in the margins of a conference in Brussels, where Lemaitre told Einstein, look, your equation predicts that the universe should have an origin, a genuine origin, not just an explosion, the origin of time. The most radical origin you can imagine, and then still a little bit more radical. Einstein didn't like it. He didn't like it at all. And why? Fundamentally, why? Because at the Big Bang, at the beginning, Einstein's equation gets also destroyed. Einstein's equation had this very strange property that it predicted its own downfall at the Big Bang, which remained, therefore, shrouded in mystery, out of science. And then furthermore, Lemaitre was a priest. So Einstein said, well, wait a minute, you're trying to get God into this business. And so that's what happened. But Lemaitre was not trying to do that. Lemaitre was, in fact, I think he thought about the Big Bang. I think he thought that Einstein was a little too conservative, and that the Big Bang was, with the discovery of the Big Bang, that we had discovered something without a cause. Because you see, if there is no notion of time, then the whole question of what came before the Big Bang doesn't make any sense. You can't even ask the question in a meaningful way. And so Lemaitre was kind of ready to give up on the idea that there should be a first cause. Einstein was worried that this whole thing wouldn't work. And so Lemaitre rather poetically thought about the Big Bang as a primeval atom, some sort of super abstract state out of which time, space, and matter would emerge. But he never wrote down any equation. This was way before this was possible. You might wonder, did Lemaitre and Einstein in the 1930s, was there any notion that the Big Bang couldn't have been anything? Was there any notion of this strange biophilic nature of the universe, that the Big Bang somehow had to be special to get the universe onto a biophilic track? The answer is yes. This is one of the most amazing scientific documents of the 20th century. These curves are hand-drawn by Lemaitre in 1929, when no one believed in an expanding universe. On the horizontal axis, you have time. On the vertical axis, you have a measure for the size of the universe. And you see all these different curves. They're all different kinds of universes. Well, none of them is habitable. None of them is biophilic. In none of them, you form stars and galaxies except in one, namely the one that goes off horizontally. And then, of course, it doesn't stop there, right? There is a second page on which Lemaitre continues. Here, by the way, Lemaitre wrote T equals 0. T for time. This is the zero of time, the Big Bang, and that is probably the very first mention in a scientific context of the idea of a Big Bang. So Lemaitre realized that there was a giant puzzle. Most of the universes sprouting out of a Big Bang aren't lifeless. It requires special conditions. But there was no guidance whatsoever on what this could be. So enjoy this graph. It's one of the great little science documents of the 20th century. So I'm going to gloss over the next decades of development of the Big Bang theory. As you probably know, the whole idea was confirmed only 30 years later, in '65, with the development of intercontinental communication, the large radio antennas, who were picking up a noise, who were picking up a faint noise, which was quickly identified as the afterglow of the heat of the Big Bang. The Big Bang was hot. The universe was filled with radiation. That radiation can't just escape, because the universe is all there is, but the radiation cools down. So today the Big Bang is very cold. It's about 3 Kelvin, but it is really the remnant of the heat of the first moments. So we have satellites today which map out the Big Bang radiation that reaches us from different directions in the sky. And this is the typical sky map of that Big Bang radiation. And you see the Big Bang flickers. The different colors represent the temperature of the Big Bang radiation. And the difference between red and blue is about a small, small fraction of a degree. The Big Bang was roughly equally hot everywhere, but not exactly. And see what happens with these tiny, tiny temperature differences of the early radiation. In the hotter regions, the blue regions, eventually there, the first stars would be born. And so you get an aggregation of matter, which eventually ignites and leads to stars and larger systems, stars would combine to form galaxies, Milky Ways, and roughly after a few billion years, you see that the universe comes in a sort of a quieter era with new generations of stars, planets like the Earth, and eventually the satellite with which we map all that. So you see, 13 billion years of evolution in 1 minute, not bad. But again, these flickers, if these tiny, tiny flickers, 1/10,000th of a degree, if they hadn't been there, none of this would happen. Stronger still, if these flickers had been just a tiny bit larger, the evolution of the universe would have produced a lot of black holes and no habitable planets like the Earth. It's once again one of these biophilic features encoded in the Big Bang, and their origin is really what that question of design is all about. So I sometimes say that the Big Bang is both the cornerstone and the Achilles heel of modern cosmology. It's the cornerstone because it works. It's a model that explains and brings together a large number of different cosmological and astronomical observations. But it's the Achilles heel because it only works if you get the universe going with exactly the right conditions. And those conditions already encode the idea that in billions of years later, there should be room, there should be conditions suitable for complexity. And if you stare at that enigma, you're sort of faced with only two explanations. One is the mathematical necessity of Newton and Einstein, and the other one is the one that Einstein complained about. It's something out of science. We can't explain this. Maybe there's a third explanation about which I'm sure some of you have heard. Maybe Einstein's theory is misleading us. Maybe the Big Bang isn't really the origin. Maybe there is not just one universe. Maybe there are many universes. Very popular in the movie industry, right? Maybe there's a multiverse. Maybe there's a giant space containing many different kinds of universes, each with their own physical laws. Many of them will be lifeless, but once in a while, you're bound to find one in which we can be. So this was the situation. This was sort of the historical context behind that. When I met Stephen. Here this is a few years later. He had changed office, as you can see. But other than that, that was the situation. And of course, Hawking himself had written a book in the 80s, a famous book, A Brief History of Time, in which he had advanced the first explanation, its mathematical necessity. The highlight of A Brief History of Time was Hawking proposing a mathematical model for the creation of the universe, which he called, or at least his editor called, the mind of God. So again, the Platonic idea that these laws of physics are really fundamental, absolute truths. So that was the situation, that was the background. But by that time, in the early 2000s, Stephen had realized that his model of A Brief History of Time wasn't working. What was wrong with it? His creation model was producing an empty, lifeless universe. And so he was revisiting this question in the light of no evidence for mathematical necessity from fundamental physics, the multiverse, which didn't seem scientific, and so clearly we were missing something. And this eventually, I think we had our eureka moment, and I want to share this with you if this works. This is how Stephen, one morning in 2006, I think, put it to me.
I have changed my mind. A brief history of time is written from the wrong perspective. We are not angels who view the universe from the outside.
So, as you can feel, talking to Stephen was very much like talking to an oracle. And I'm sometimes asked, well, how is it even possible to work with him? I mean, this is insane. But you see, the thing is, this is just what research is about. It's a lot of confusion and the occasional insight. And so I view my collaboration, and I've tried to sort of frame my book in the same way, as one long, winding conversation with one idea building onto the next one. And it's this whole package over 20 years which is really conveying sort of the core of our collaboration. One single conversation would often go nowhere. But there were all these other conversations floating in the back of our minds, which meant that eventually, I think, we were trying to put a few pieces together. But what is this about? Well, look, we have this biophilic universe. And for decades, even for centuries, physicists have tried to understand this by taking a distant, objective viewpoint. Physicists have developed a real knack for looking at the world as if we are outside. That started with the scientific revolution, with Copernicus, who put ourselves outside the solar system. It continued with Newton, who put this objective viewpoint into our equation, and it culminated in the multiverse, in which a cosmologist put himself out of the not just the universe, but out of the many universes. And in many ways, this is the success story of physics, the ability to look at the world objectively. But when it comes to this deeper question, when you probe the biophilic nature of the universe, we've reached the limits of this model. We must recognize within physics that we are within the universe and look around. And that's the change of perspective, which took us years to realize, I'm sorry, but which is crucial when it comes to getting a grasp on this design question. So the thing is, how do you then do this? How do you turn cosmology inside out? How do you ingrain the simple fact that we are within the universe into your mathematical framework of physics? Well, in fact, we were much inspired or helped by a completely different corner of physics, quantum theory. And so from then onwards, Stephen and I really try to fit these two together. Quantum theory is a theory that describes the microscopic world, the theory of particles and atoms. It's a theory that talks about uncertainty, probabilities, randomness. It's a very different kind of physics than what we know from Newton and Einstein. Here are two of its founding fathers, Niels Bohr, left, and then Albert Einstein. He seems to be in a better mood here. And it's one of the weirdest features of quantum theory that it abandons this objective Archimedean perspective onto the world. An act of observation in quantum theory is not something which happens from nowhere, so to speak. No, it's always an interaction. And the kind of interactions, the kind of questions we ask influence how reality manifests itself. And so that's a very, very strange feature, but it's crucial when moving forward. Take an electron, a single particle. An electron will not even have a position until you ask what its position is. So quantum theory somehow describes reality at some pre-existence stage. Same with Schrödinger's cat, Schrödinger's famous cat. There it is in 2 dimensions. It's not quite dead or alive until you ask whether it's dead or alive. And in fact, it's this kind of weird feature that Einstein didn't like about quantum theory. Einstein wanted, evidently, a theory of physics, a framework which gives us objective truths, independently of whether the reality is observed or not. But Niels Bohr embraced this idea. And Niels Bohr would have said, well, no phenomenon is a real phenomenon until it's an observed phenomenon. So you could say that, in a way, that Niels Bohr is the René Magritte of physics. René Magritte, another Belgian, amazing. You see him here painting himself, painting a bird, while looking at an egg. Magritte is drawing, is painting the possibilities, painting the potential. He's trying to say that engaging, that observing is engaging with reality, is realizing reality. So he's, and well, in many ways, this is how quantum theory works. The theory describes, as I said, the micro world at some pre-existence stage in terms of wave functions and so forth. So Stephen and I, essentially, we just ran with this idea. We took the quantum theory, describing a successful theory of the micro world, and we said, okay, if the big universe at the Big Bang becomes very small, quantum theory, the quantum perspective onto the world, is becoming crucially important. And so we developed our own cosmic version, if you wish, of Magritte. Here it is, the U for the universe. The universe starts out at the Big Bang on the top right corner, it expands, but then there's this I, then there's this act of, this quantum act of observation, which, with the dotted line, kind of realizes the past. There is no definite history, one thing happening after another, until it is an observed history. Mind you, this does not need to be a human observer, of course. Anything is observing all the time in the universe. The universe is observing itself in many, many different ways. Even a single photon can perform an act, a quantum act of observation. In fact, your kids will certainly know the Harry Potter books. The whole thing is a bit like this blank diary of Tom Riddle in the Harry Potter books. This diary knows the answer to all sorts of questions, but it only gives you an answer when you ask a question. That's the way quantum theory works. So, what happens? What happens then when we take our quantum viewpoint and we look back into the Big Bang, into the chamber of secrets of the Big Bang? We go back in time towards the Big Bang. If we were doing this in Einstein's theory, as I said, we hit a wall. We hit a wall where science breaks down. If we do this in this quantum thinking, something different is happening. The time dimension gradually fades away. In fact, it sort of combines with the space dimensions and to round off the universe. It's the past, the far past, is almost like a sphere. And so the name of our theory is also the no-boundary theory. It's rounded off in the past, where the laws of physics are still. So asking what came before the Big Bang, it's very obvious in this picture that it doesn't make sense, because it's the dimension of time itself, which if you go back towards the past, evaporates, fades away. But that transition, which I've sketched there, is in fact the ultimate transition of a whole deeper level of evolution that is playing out in these earliest phases. This is an abstract picture of the first fraction of a second of the evolution of the universe. You see the laws of physics that we have today up there. We go back in time towards the bottom of the slide. What is happening? These different forces that we have today, the different particles, they unify. They lose their identity. Physics simplifies. And we've always thought that we would find a solid foundation, a final equation, a master equation governing this whole process. But the crux of the cosmogenesis that Hawking and I developed is very, very different. It's that this process of simplification continues all the way down till eventually also the time and space lose their identity. So this tree of laws, which branched out in the first stages of the universe, of course reminds us of something. It reminds us of Darwin. It reminds us of the tree of life, of Darwinian evolution. And indeed, this amounts, I believe, to somewhat of a Darwinian turn to cosmology. So we have these two great sketches. On the left, you have Darwin's first sketch of the first sketch of his tree of life, just when he returned from the Galapagos Islands. On the right, exactly 1 century later, we have one of these sketches by Lemaitre in one of his notebooks of this biophilic expanding universe. Now, for 90 years, we have tried to understand these two types of evolution, biology and cosmology, on a completely different ontology. Darwin is emergence, is evolution, chance, variation. Lemaitre was always thought to be founded in timeless, eternal, objective laws. The crux of our hypothesis is that this distinction is not right, that these are, in fact, two very different levels of one giant evolutionary process. So that's the crux of our hypothesis. That's a brief intro to what my discovery journey with Stephen was about. As I mentioned, it started about 25 years ago. This is when we were in Brussels, and it ended, of course, with Stephen's passing on March 14, 2018. Stephen's ashes today are buried in Westminster Abbey, in between the graves, in fact, of Darwin and Newton. I don't think the app knew what he was doing, but it's so incredibly fitting, right? In a sense, our hypothesis unifies Newton's rigid mathematical thinking with Darwin's giant idea that there's a unity in nature. And so the title of my book, in English, On the Origin of Time, and I can gather that it's roughly correctly translated, is of course a direct reference to Darwin's title, On the Origin of Species. And I've tried to write it in the same way. Darwin's book offers a grand new hypothesis written for a broad audience, and I've tried my best to do the same here. Now, in the last few minutes, let me look towards the future. Where do we go from here? How do we test this hypothesis? This new level of evolution happens in the earliest stages of the universe. How can we possibly find fossils of that remote epoch? Well, I don't have many ideas, but we have one. Remember Einstein's equation. Here it was. This dialogue between space and matter. If this equality, this dialogue means that if you shake the matter, space is going to shake too. That shaking, these waves, these are gravitational waves, these are ripples of space-time. Well, those ripples, unlike light waves, those ripples, those gravitational waves, they travel through anything. And so in principle, we should be able to detect gravitational waves from these early stages, from this branching process of the tree of laws. Each of those branchings goes together with a burst of gravitational waves. Those gravitational waves, just like light waves, they fill the universe today, but they're very, very, very weak. And so we haven't observed them, we haven't found them. But there are these missions, there are these giant European missions in progress to prepare for measuring those waves from the Big Bang. This is LISA, a European Space Agency mission, 3 satellites orbiting the Sun, capable of capturing gravitational waves from the Big Bang. And then there's a complementary mission called Einstein Telescope, which is an equivalent which goes underground. It's an observatory that would sit underground, once again designed to detect minute ripples of space. You always do this in triangles or Ls, because gravitational waves, ripples of space, are ripples of length. They are ripples of length, and so you have to measure length. There are no particles involved. It's pure space, pure geometry. And so, of course, we have measured gravitational waves, but that is just the tip of the iceberg. What these missions are about, they're about unlocking the entire universe, the deepest regions where light cannot penetrate, such as the primeval epoch after the Big Bang. More fundamentally, there is a kind of epistemic readjustment in what I told you. Physics was always about laws of evolution, dynamics. Questions, observations, boundary conditions, questions about origin, that was never part of the laws. It was always part of the context of the environment, outside of the laws. But of course, I've tried to crack open physics. We've asked questions about that biophilic universe which have required us to open our mind and to say, wait a minute, maybe this was not the end of what physics was meant to be. Maybe there's a more general notion of physics which includes, which intertwines boundary conditions, dynamics, observership in a new whole. And that, how that whole plays out, that's the refinement really of our hypothesis. It's really the question about how quantum theory and gravity fundamentally work together. There's lots of evidence that this comes together with looking at the world as a hologram. You know that in a normal hologram, there's a third dimension of space opening up, popping out of a screen. Well, theoretical physicists have since 20 years or so are so keen on holograms because that seems to be the way that gravity and quantum theory work together. This would be sort of a cutting-edge representation of the evolution of the universe. Today, we're at the boundary of this disk, and the past is emergent towards the interior. And the way you would reconstruct the past from this hologram on the boundary would be by slowly taking a more coarse-grained view. Time, the past history, would be fundamentally emergent in this new physics, which is, in fact, in retrospect, it's just what the doctor ordered, because the dimension of time was the problematic one all along. So the equation behind this, Stephen and I wrote down an equation behind this. That equation allows you to go back in time all the way to the Big Bang, but at the Big Bang, ultimately, when time runs out, the equation turns silent too. The Big Bang becomes, at the same time, some sort of epistemic horizon in our hypothesis, a true origin, an origin of time and an origin of laws. And of course, there's a certain finitude associated with this. It means that there is not this solid, rock-solid master equation. There's almost no foundation. It's a point, strikingly, made by Hannah Arendt 50 years ago. Hannah Arendt, the German philosopher, wrote a book, The Human Condition, in which in the second part, she's asking the question, wait, what are the fundamentals of science here? I can't see how science can ultimately be truly objective, independent of our human condition. Even fundamental physics, she argued, must in one way or another encode this basic fact that we are looking up and around from within the universe. It must encode the finitude that comes with this. And so, in my wildest dreams, I think that the hypothesis that I advanced with Hawking is a response to iron's concern. It builds into fundamental physics, in its mathematical framework, the basic conditions that allow science to be possible at all. And so that's, I think, deeply the humanist drive that I've seen so often at play when working with Hawking. Thank you.
Ge en stor applåd till bandet Backlura bestående av Palle Sollinger på bas, Daniel Fredriksson på trummor och Carl Olandersson på trumpet.
Ya me canso de llorar y no amanecer, ya no sé si maldecirte o por ti rezar. Tengo miedo de buscarte y de encontrarte. Donde me aseguran mis amigos que te vas. Hay momentos en que quisiera mejor rajarme y arrancarme y a los clavos de mi pena. Tengo mis ojos sin morir, sin mirar tus ojos, y mi cariño con la aurora te vuelvo a esperar. Y agarraste por tu cuenta la parada. Que honra parandera. Si tus caricias han de mía de nadie amar, y aunque te amo con locura parandera.
Stephen Hawking, he died, as you might know, the same day as Albert Einstein was born, which is fascinating. March 14, the International Pi Day, you know, the mathematical symbol of pi. Okay, Thomas, please come back on stage. We're going to talk about your work, and we're also extremely happy to have a second guest on stage, the professor of physics, author of many books in Sweden and well known from radio and television. Please welcome Professor Ulf Danielsson.
Tack, tack.
Okay. And please help yourself with water. You might need it because now we're going into a tough discussion on Thomas Hertog's presentation. Ulf, first, I mean, how much does Thomas' work relate to your research? Are you doing the same thing, or are you working in different areas? Or please elaborate.
I mean, roughly, I would say that we are probably working in the same area. Maybe not on the same specific problems, but we are working on sort of quantum gravity, string theory, cosmology, black holes, the really fundamental questions. So in that sense, we are rather close. I think that we can sort of understand each other's language and so on. And this has been very, very interesting to listen to, and obviously I have some criticism and questions and so on, but
okay, but first of all, do you share Thomas' view of a Darwinian evolution process of the universe?
Well, that is, of course, a very difficult question to contemplate. Actually, there are some things which I really liked, and that is this reversal of perspectives. Because a real sickness, I would say, in theoretical physics, string theory in general, is this obsession with mathematical beauty. And the idea that it's sort of symmetry and mathematics is something which is outside of our world, and we are supposed to be finding these almost divine laws which are coming from some Platonic reality outside of the universe. And that is not, I think, a very reasonable way to look at things at all. So turning things outside and in, that's something which I really find I'm very sympathetic to. And in fact, that also brings really the interplay between us as physicists and the real world, experiments and the modeling coming back into center. Because what are we doing really as human beings or scientists or whatever? We are exploring an unknown world and try to understand it as best that we can. So we really start here, and then we work ourselves outwards and also backwards in time and try to use mathematics, which is not out there or not outside the universe, it's not in the universe. From my point of view, it's inside of our heads. It's a tool to study the world to the best of our capabilities. So in that sense, I think we are probably on the same footing.
That's a start.
That's a very good start. But then I'm not really so sure anymore, because you asked this thing about the Darwinian evolution. If you go back to Darwin, he had actually a lot of observational experimental evidence for his thesis. I mean, it was not that he just got this idea and that everything was sort of coming from evolution or history. There were actually lots of very concrete evidence in support of his theory, and he traveled around the world in order to gather such support. I mean, you could look at the domestication of animals. You could
went to the Galapagos.
And look at these finches on these different islands and so on. Lots of evidence where you could actually see this kind of evolution. So it was a need of he saw that there was a history, and it was a need of an explanation. When it comes to cosmology and the origin of the universe, we are in a much worse situation, I would say. Because we don't really see anything of that. Obviously, we see an evolution in a rather historical development of the history of the universe. But unfortunately, it's the same physical laws which apply with high accuracy all the way back, and there is really no change. I know that you would say that it's much, much earlier that these things happen. But then again, we don't have any evidence for that, which means that one can cook up this kind of idea, and it sounds very attractive from a philosophical point of view and so on, but we have no idea whether that is true or not. It's as unfounded, really, as these mathematics, appealing to mathematics outside of the universe, or we could come back to the multiverse, which you also criticized, rightly, but on the other hand, that's also, in some sense, very in some sense, very conservative way of looking at the universe, because we have always been constructing a kind of multiverses. I mean, the first human beings exploring the countryside, finding a hill, something on the other side of the hill, a sea, something again on the other side of the sea, new continents, look up the stars, other planets. The universe or our world is continuously growing, and there is always a new horizon to cross. So to say that this universe that we now see is everything, and we are now in a position to explain everything by just looking at this, that is not necessarily the right point of view either. So the idea of a multiverse, which lots of maybe different physical laws and so on, that is actually quite a natural assumption, which you could see then, you could again go back in history and think about Kepler and Newton, Kepler trying to explain this single solar system out of mathematical consistency and beauty. Newton finding, no, there are laws which apply to many different kinds of planets and stars in the whole universe. And from that point of view, the multiverse is also very natural. But again, it's just a hypothesis. And we don't know, because we have so little data, and we know so little about the thing that we want to explain. We don't know what dark matter is, we don't know what dark energy is, and that's 95% of everything. And then we try to explain, well, the origin of what exactly? We don't even know what we are trying to explain.
Okay, Thomas, before you reply this, which I will definitely let you do,
thank you,
but first
I came all the way from Brussels.
Exactly. But
I came all the way from Uppsala.
From Uppsala. But before you do that, does beauty play an important role in your theorizing?
Yes and no. Beauty, I would say mathematical consistency plays a role. And this is my criticism against the multiverse.
Okay, please go on.
The multiverse does not make unambiguous predictions. It suffers from the measure problem. It suffers from the problem that it doesn't tell us in which one of these universes we should find ourselves. And so it's not science. It's not a scientific hypothesis. In fact, this one that I developed with Hawking came out of the paradoxes of the multiverse, which after thinking about it for a while turned out to be so deep, so profound, that you have to conclude this is a dead end. But of course, I agree with you that this whole new way of conceiving of the origin, which includes then the origin of the laws, is theoretical physics at this point. The evidence, the fossils are so far hidden. But it's a hypothesis which, to answer your question, emerges out of seeking a mathematically consistent framework for cosmology, which I claim the multiverse is not. Whether these fossils will remain hidden forever, we cannot say at this point.
But in what sense is the multiverse not mathematically consistent, you mean?
As a physical theory? Well...
It's not empirically, there's no evidence.
Oh, no, it's worse.
It's worse, okay.
Obviously, you can't go to another universe to check it out, right? Except in movies. No, the problem with the multiverse is that it's again a theory which takes this God's eye viewpoint, as if we're outside, we're looking down on maybe infinitely many universes, but the theory, the mathematics of the multiverse is not telling us in which one of these universes we should be, and therefore what we in this universe should be observing. So it doesn't make unambiguous predictions. If you believe a little bit in Popper, this is
Karl Popper.
So it's not testable in that sense.
It's not falsifiable.
Not falsifiable.
Could I?
Yeah, sure. But first, Ulf, I mean, you have been working with string theory for quite many years. You have no empirical evidence whatsoever for string theory.
In fact,
so what's the difference?
No, I agree completely. And actually, I can tell. I mean, Thomas here knows that I've been working for the last 15 years with one of your colleagues, trying to disprove the string landscape, and in fact criticizing the models which have been one has trying to construct the landscape on over the last decade or so.
Yeah.
And I agree completely that as far as what the mathematics of string theory has been able to deliver, there is very little to so far to be very proud of. If you think of the multiverse as the general idea, it's no different from what you could have explained. I mean, you could go back to the 17th century, you could talk with Giordano Bruno or someone like that about the possible of many, many other worlds and the fact that the Earth is not unique, and we should not try to find an explanation for why the Earth at this or that distance from the Sun. It's just pure accident. There are many, many different worlds, and we are living in the one where, per accident, there happen to be the conditions be suitable for life. So the multiverse is, in that essence, from a philosophical point of view, no difference. There is no difference. And you could, again, criticize whether there is a predictability or not. Then, of course, there is another parallel as well. If you think about the physicist astronomers on the 17th or 18th or even 19th century, they didn't have any way to probe conditions at other planets around other stars. That was absolutely impossible. I mean, for instance, Auguste Comte, the philosopher, physicist, said somewhere, we will never know about what the stars consist of. About the same time, spectroscopy was discovered. So we don't know what the future will bring from that point of view. So from a philosophical point of view, I don't think that one can criticize the multiverse with Karl Popper and so on. But from a mathematical point of view, I do agree that there's very little of predictions coming out of it. And that is because there is another very, very difficult problem that we probably need to solve first, and that is to be able to explain the presence of dark matter and dark energy, which turns out to be such an extremely difficult problem in string theory, much more difficult than one thought from first hand. So I think there are many more concrete problems. What is our universe actually consisting of before we in any really trustworthy way can start to explain from where it came?
Yeah, your reflections?
My feelings? No, but there's a certain level of agreement here indeed. I am not so much criticizing the multiverse as a... I'm not quite sure what you mean as a philosophical idea, but one could mean the possibility of many different kinds of universes, maybe up in a mathematical realm or whatever. I'm certainly not criticizing that. I'm criticizing the sort of more low-key idea, which the slide showed, of a giant space filled with bubbles, which is out there, and we're sort of lost. The key point is the following. In this Darwinian way of thinking, whether or not there are other universes doesn't play a role in the predictive framework of the cosmological theory. Just like Darwin, even though there is probably life on other planets, it doesn't matter to study the tree of life on this planet. And that has everything to do with the fact that in this quantum thinking, we are putting ourselves within this universe. So if you wish, the other universes, they may or may not be out there, but they're sort of lost in quantum uncertainty, perhaps as possibilities, perhaps as potential worlds, but they don't interfere with the way we hope to find predictions or correlations within this universe. And I sort of disagree with you that it's too early to do that. Some of our colleagues say it's too early to think about it. But I disagree, because this kind of hypothesis is essentially, in our more technical language, a hypothesis on the origin of inflation, how inflation started, and it assigns probabilities conditioned upon where we are. You need a completion of inflation, a quantum completion of inflation, in order to refine its predictions. And I do think that it's only that way that we're going to be able to really interpret our future observations and probe and look that early era.
But before you answer, I want to ask you both of you a question here. I mean, multiverse theory or string theory or any variants of this, I mean, there is no evidence for anything of this. There is no empirical, it's not testable, it's not falsifiable. in what sense is it even a scientific theory? I mean, in what way does it differ from an hallucination?
No, but I mean, there's something very important here.
Just trying to provoke a little bit.
Yeah,
here.
no, but it's...
No, we agree.
Yes. But it's not... I mean, the point is that there are two very important facts, in a way. One fact is that gravity and quantum mechanics doesn't really love each other in some sense. There is some problem there.
Yeah.
And that means that our fundamental theories, they don't really talk to each other. There is a theoretical problem here. There has to be something new, something which helps these theories to work together. So that means that there is theoretical motivation to, there has to be something more. Then, on an observational, experimental point of view, there is some very suggestive evidence that there is something lacking, and that is indeed dark matter and even more dark energy, 95% of the content of the universe. So that means that
it's not evidence for string theory.
No, not at all. But it means that we have to think about these problems. We have to work on quantum mechanics and gravity, because we probably agree that that is something which is very crucial to understand the cosmology, the origin of the universe. So if one finds that these are questions which are worthy of study, then one has to do something. One has to try to find ways to combine these theories together, and that is really what string theory does. It's true that it hasn't really delivered any concrete predictions as yet. You could blame the difficulty in making observations and experiments, but what's there is a lot of very intriguing mathematical consistencies. So it's a model toolbox which is sitting there and it might be possible to apply it to the real world if we get enough data. So it's at that level. It doesn't mean that this is necessarily correct. It might be a first step towards something that will actually describe the real world. And the point is that the only way to make real progress is to enter into some kind of dialogue between observations and theory and experiment, as it was in the early 20th century when quantum mechanics was developed. Unfortunately, all these observation experiments are so difficult to do. So we are sort of sitting here and trying to think our way through, and that will never work. I agree with that. But we have to have new data, and hopefully maybe gravitational waves or something else will give us that.
But Thomas, if I rephrase my question in a little bit less provocative way, if you have a theory, a scientific theory, that actually is not testable and there is no evidence or empirical evidence, what kind of arguments do you think is valid for that kind of theory? I mean, is mathematical consistency an argument, or what kind of argument? This is a philosophy of science question, actually. How could you argue for a theory that is not empirically testable?
You can't. You can develop a theory, and mathematical consistency, as Ulf says, will be your prime guidance. Paradoxes are the driving force in our field, because paradoxes point out all sorts of little inconsistencies, or some major inconsistencies, in attempts to combine quantum theory and gravity. But ultimately, so these are our guidance, these are our experiments, these are our thought experiments, if you wish. But ultimately, the real test of a theory is, of course, its confrontation with observations. I seem to be, among the three of us, the most optimistic on that front.
I just ask questions.
Yeah, I could see that. No, but for instance, a concrete prediction is of this cosmogenesis that I developed with Stephen is there's a lot of inflation. There's a burst of extremely rapid expansion in the earliest phase of the universe, and that comes together with a burst of gravitational waves. Those gravitational waves may be very difficult to find, but if our hypothesis is correct, then they must be there at some level. That's quite a clean prediction.
Yeah,
at some level.
Yes.
Yeah, always around the corner. Or, I mean, is there a precise prediction of the magnitude of it?
If we combine this kind of thinking with And then it becomes tricky, of course, with information about the microscopics of one or another corner of the string landscape. Then you can refine your predictions, of course.
Okay.
But
is it falsifiable?
No physical theory is ever completely falsifiable. You're going to find evidence.
Well, I mean, it depends. You mean that it's not falsifiable because there are always some theoretician that come up with some way to tweak it?
Yeah, it's falsifiable that in a sense, in contrast with the naive thinking about multiverses, this at least makes unambiguous predictions. Give me a model and I give you a prediction. But where to look for, where are the fossils? This is, of course, in a sense, the $1,000,000 question.
But it's the gravitational waves.
The gravitational waves would be one, the primordial gravitational waves would be one corner. Another corner, maybe it would be, okay, these laws of physics, as you mentioned, they seem to be pretty stable for billions of years. There seem to be hardly any change. But perhaps when cosmological observations get better, we do find, nevertheless, for instance, in the dark energy, tiny, tiny traces of changes. So the idea that the laws of physics, once we find a single piece of evidence that the laws of physics, like dark energy, haven't been completely fixed, I think we can slowly begin to change our view.
The dark energy being constant, that's sort of an approximation. You don't need to think about evolution to have a dark energy which is changing with time. I mean, that's part of what people are reasoning in terms of the landscape or inflationary models within string theory. So that has nothing really to do with that. Also predictions about gravitational waves. So it seems to me that what you might cook up is a model that produces inflation, a very particular model, maybe testable, and you can, and so on and so forth. But it doesn't tell you too much about the core idea, which is this evolutionary thing.
The real evolutionary, that's right, the real evolutionary aspect comes all the way at the beginning when you transition when your time dimension disappears, when you really transition into that, I know how to explain it to you, but when you transition into that timeless realm of the no boundary hypothesis. But there's another way. Think about holography. Suppose the whole holography is a new way of combining quantum theory and gravity. It comes out of string theory. Suppose one day we really understand how that holographic way of thinking about the world applies to cosmology, applies to the universe. At that point, at least with what we understand today about holography, time will be in the emergent dimension, and that in dimension going into the past will essentially evaporate, will disappear. Suppose we theorists get convinced that this is the way holography works. Then this evolutionary layer that I talk about will be almost inevitable because it's built into holography. Holography predicts there is a limit to which the past extends.
Let me ask you another question, changing focus a little bit. You showed this very well-known picture of the eye watching, from John Wheeler, right? I think he made that drawing in 1979, the Wheeler eye, watching the origin of the universe. What exactly do you mean by that? that the observer is a part of the physical theory? Because I guess you don't mean that you need consciousness for physics to work, because that's a bit of a new age interpretation of
as I think mechanics. I said, it could be a single photon.
Okay, so you mean a single photon could be the observer?
Anything is, the environment is performing quantum observations all the time.
But in what sense is it an observer if it's not a conscious observer?
It's an observer in the sense that it interacts, and that interaction causes the quantum evolution to branch one way or another. So it crystallizes
the collapse of the wave function.
Yeah, it's a way of describing. Okay, what Wheeler was trying to do was indeed. Wheeler's student was Everett, who came up with the whole many worlds
theory,
right? Yeah.
which is something else than the multiverse. It must be said.
Yeah.
Yeah.
So what was I trying to explain?
No, what is the observer? What does it mean that we are a part of the...
So what Wheeler tried to illustrate with this picture is a more holistic way, a more general way of practicing quantum theory, where we do not assume the observer is outside the system in an external, classical, definite world, but is part of the system. And then you cannot talk about the collapse of the wave function, because the collapse of the wave function is induced by an external actor. So Wheeler tried to convey the idea that observations carve a tangible reality from within, from what you could call a realm of uncertainty, which is this wave function.
But I guess you mean that that would be the case even if we weren't around. I mean, living beings.
Sure.
So it's not dependent on life.
Sure. No.
Okay.
But I have to ask you about this evolution in the early universe. How does it happen? What is the selection principle?
It's the quantum act of observation.
But who's observing what?
The early universe is observing itself.
And what is sort of the survival of the fittest here?
Once you get into a branch, as you know, once a branch crystallizes, once you have, so in other words, once the system chooses one way or another, the next evolution builds on the first, on the former branchings. So you don't, in any kind of quantum system, right? Your branching gets frozen in. So this is what people like Everett and Gell-Mann called frozen accidents. There's a certain level of randomness associated with quantum dynamics, but once interactions choose one branch or another, that accidental branching is frozen in. And in physics, you can then build on this and with future frozen accidents. So in a way, the picture that emerges here is that this evolution is the result of an enormous number of accidents which got frozen in, just like the structure of the DNA molecule got frozen in and became a rule of life.
But then
Ulf, wait, just to make sure that the audience is with us here, because you have to explain. You have to explain how does Everett come into this. I mean, to Everett's idea of many worlds, that's not what you're saying. You don't subscribe.
I think he is.
Everett is, of course, yeah, sure. At that level,
He is
okay, but explain the many worlds theory then for the audience. What did Everett say? He said that each time this wave function collapses, it's created two realities, or many realities.
These are the branches you're talking about.
Sure. I'm not sure what words Everett used. Probably not those words. But indeed, instead of having an external actor collapsing the wave function, Everett would say that the wave function describes all possible histories. Possible histories. Everett would not go as far, and certainly after Everett, people would not go as far as saying these histories are all real out there. But it's a way of describing the...
But you need them in order for the selection principle. You need all of these different branches, and then some selection principle that does what?
No, I need frozen accidents.
What is a frozen accident?
It's
Don't get too internal here. What is a frozen accident?
It's the result of an act of observation.
And an observation could be a physical interaction of any kind.
For instance, crystallizing in the early universe, one set of forces, a certain set of particles, a certain property of the universe.
But why would this lead to a universe full of stars and planets and life?
That's a question. That's not what I'm saying. That's not at all what I'm saying.
It sounded like you were saying that in the talk.
You're asking for a prior explanation. I'm just like Darwin. I am not giving a prior explanation. Darwin did not predict how the tree of life this tree of life. Darwin looked around for fossils and reconstructed the tree of life, assuming a genuine origin. I'm looking around and I'm reconstructing the early universe, starting from what we have today.
But
This
you
is a
also
key
claim that
point.
this is a way to... That was Hawking's question, right? There seems to be design. Why is that? So then it must be that this is supposed to be explaining the fact that the universe is so special and also nice to living things somehow. And then I ask you, how can this explain that? Because you said that in the talk, that was what you wanted to explain with the theory.
Sure. And
So how does it work?
It's a pain in the ass, you know.
The explanation is that it is not a prior mathematical truth and the result of an evolution which includes a random component.
But why does it how does it explain this design thing?
The explanation is, once again, not prior, but in retrospect. So you may not like the explanation, but because it doesn't tell you that it had to be like this. Just like the tree of life could have been completely different, our universe, the physical laws, could have turned out to be completely different. So instead of a rule that gives us a prior explanation like Einstein thought, we are advancing the idea that it is a fundamentally evolutionary emergent process, just like, once again.
But Thomas,
just
can I
like
ask
biology.
you, I mean, the fine-tuning argument that you sometimes hear, how can our universe be so fine-tuned so life could emerge? Ulf's multiverse theory explains that quite easily because...
No, it does not.
Okay, you're going to tell me why very soon, but as I interpreted it, there could have been millions of universes that doesn't create life. They were tuned in many different ways.
Like billions of planets.
Yeah, but one universe actually was tuned for life, and obviously we have to be in it, obviously, because we are that kind of life. In what sense doesn't the multiverse explain the fine-tuning argument?
Because it doesn't make any predictions.
No, but that's not what I mean. I mean, if you don't have a multiverse, then it must be difficult to explain how the universe can be so fine-tuned for living organisms to evolve, unless you think it's designed by a god.
If I phrase it like this, if you take the Earth here, why is Earth so nice to living creatures? Why can there be life on Earth? I would say that the explanation is anthropic, in the sense there are so many different planets around.
Without life.
Without life. And some have life just because the planets are sitting in the right spot. It's just at that level that the multiverse explains, quote unquote, the fine-tuning problem. But of course, there is no real theory for the multiverse. So from that point of view, it's more like just that someone in the 15th or 16th century could think about the possibilities of other planets without having Newton's mechanics to explain their presence, to describe their presence.
As you know very well, the multiverse, many models of the multiverse predict that we should be just a fluke in an otherwise empty universe. It doesn't explain a damn shit about our universe.
But that's just because you are trying to. I mean, obviously, there is no
It's
theory.
enough just to have a solar system. Why do we need all these other galaxies?
But then why are you trying to explain this universe? It's just enough to have this universe. Why do you even bother to get a theory to try to explain it?
Because I start from our universe, and I'm trying to find a model that explains its history, and in doing so, we will identify correlations between different features of our universe, which we can potentially observe.
Let's make a thought experiment here.
Yeah,
we are in a different universe. We have the Earth orbiting the Sun, but everything is in a big cloud, so we don't see anything of the rest of the universe. You are sitting now on the Earth, trying to explain the origin of the Earth. thinking of some quantum origin of the Earth in the proto-nebula with the sun, which sort of evolutionary made this Earth come out as it is with oxygen and water and whatever in order to prepare it for life. That's sort of a parallel there. You are limiting yourself to one universe and try to explain it. And I could imagine you sitting on the Earth in this black cloud where you don't realize there are other planets around and trying to explain somehow the origin of that single planet and why it has the properties that it has. I cannot see any difference.
I see the
there,
confusion.
really.
I see the confusion, but there is a difference. You might say, okay, where are these other universes in my theory? My claim is that they are. Yeah, I cannot say it. My claim is that they're in this wave function, but that they're lost in uncertainty. In other words, that the quantum randomness is too large to say anything concretely about these. So this interpretation of the no boundary hypothesis that's behind this is that it's in a way a huge coarse graining of a history in which this structure of the multiverse that is not definite, but it's more like your cloud of uncertainty. So I claim that quantum theory, a proper quantum view of cosmology, will ultimately teach us that there may or may not be other universes out there, but we cannot say anything about this. Quantum theory protects us, when you apply it to the universe, protects us against saying too much. I claim that contemplating a multiverse is pushing far too much this Platonic way of thinking about cosmology.
Not necessarily.
And that is different from, indeed, as you say, or with your analogy, that's different, right? Because there quantum mechanics doesn't come in.
Do you mean, when you say this, that the uncertainty of the universe is a sort of fundamental character of reality? It's not just a question of what we know.
Yes, I mean that globally our cosmos, that we are sort of having a bubble around us about which we can say something, which is a tangible, concrete reality. But there are limits, and quantum theory essentially offers us a way to not say too much.
But I asked the same question again, because I definitely got the impression that what you tried to argue was for some kind of an explanation of the fine-tuning problem. So I ask you again, what is the explanation? Why is our universe so fine-tuned?
The why is wrong.
Hawking asked exactly the same question. That was
that was 25 years ago.
Okay.
He changed his mind.
No, that was before he's changed. After he changed his mind, I think, wasn't it?
No.
Okay.
I met the old Hawking.
Okay, that was the old one. Okay.
That was the old Hawking talking, yeah.
Okay, so your answer is it's the wrong question, and I should be happy with that answer, that it's the wrong question.
Well, you should at least be happy enough to read the book.
Yeah, sure.
But Ulf, don't you agree that, I mean, quantum physics tells us that there is an inherent uncertainty in the quality of reality?
Absolutely.
It's an ontological problem, not only a knowledge problem.
Absolutely, it's very, very interesting, and it's also interesting.
That's Schrödinger's cat.
Yeah, for technological applications, you don't need to go to the early universe. It's in our surroundings here. There will be lots of really exciting things happening in the future. I'm sure about that. I also think that quantum mechanics is very important to understand the origin of the universe. All of that I agree, but I still cannot understand really what is the concrete idea.
Okay, but let me ask you another question now, because your book is called on the Origin of Time, Om tidens uppkomst. In what sense can time actually begin? You have to explain this to us. How should we understand it intuitively that you can't talk about before Big Bang, for example, because there was no time? What does it mean that there was no time? What does it even mean?
That was already in the brief history of time. The
it's like, it sounds psychedelic.
Well,
what does it mean?
I mean, you can take the analog with the
sure.
South Pole. I mean,
I-
what is south of the South Pole? What is before the first moment?
Well, but you need time for any causal event at all, for example. If you have no time,
yeah.
you can't have
No
causation.
time, no causality. I mean, yeah.
No events.
But you asked for an intuitive explanation, so I was trying to look for an...
But you
I
can't
mean-
have any existence without time.
Sure, yeah.
You agree with that? There is nothing exists without time.
The good thing with what you
Do you agree?
are saying is that you also agree that there are no equations before the beginning of time.
Yes, so...
I saw that on the seaside there. They were being removed there.
I
And
was
that I
wondering-
like. That
really?
I like.
I was wondering about that.
No,
whether
that
you
I
were right.
like.
I see.
That
So
I
because
like.
this means no single master equation for the string landscape.
Yeah. Well, no. But that depends. No, you see, because now you are confusing the model with reality. I don't think. I mean, all what we are doing is constructing mathematical tools to describe either the Earth, other planets, make predictions about those, possibly also something beyond what we call the cosmological horizon.
Yeah.
All of this is just mathematics, which, in order for it to be useful, have to lead to experimental predictions somehow.
Sure.
That also goes for string theory. So there is no difference there. But it also means to me that those equations, that string landscape, quantum mechanics, Newton's laws, whatever, they don't exist. They're just models of a universe which I agree with you, are observing from within. So there we actually agree.
But then you're very close to agreeing with this Darwinian thing, because if the equation has the property to, within it, encodes, it disappears at the Big Bang?
No, it doesn't.
We are
It doesn't disappear because it didn't exist. It didn't exist 1 billion years ago either.
Well, the equation...
the equation that they don't exist.
But I still want an answer to what exists before time. I'm not going to leave that before we end.
Well, we are going to leave that.
No, but then I will try. Then I will actually try to disagree a little bit here, because
As you haven't done already.
because I don't really see any need for a first moment like that. There might be a first moment that is identified with the creation of our universe.
Okay, yeah.
That could be, but
okay.
there might equally well be something which is before then. I think it's a very...
But Thomas wouldn't say that.
I agree, but it's a very... I mean, it's just a guess to say that didn't have a beginning or it had a beginning. We don't know. We simply don't know. We don't even know what most of the present universe consists of. And certainly we don't know whether there was a first moment.
Okay, what do you think, Thomas, about the origin of time?
We don't know.
That's your title of your book.
Well, so two things. I think the real, when you go deep into the Big Bang, that this evolutionary character of the physical laws will manifest itself. The most precise way that I know of today to read this, to see this, is indeed to take this holographic viewpoint in which the past history emerges from a holographic representation of our reality that is contingent, that encodes our observational situation. This holographic business, this holographic physics, how does it work? I think it's the beginning of a real revolution in physics in which information plays a much more central role than what it has to till today.
What do you mean by information?
Quantum information, quantum entanglement, all sorts of quantum information. We used to think about matter and space and time as being fundamental in physics. There is some evidence that this is shifting towards an information-based view of physics. And then, if you look at it that way, what is happening when you go back to the Big Bang is that simply you run out of bits encoded in your laws, in your holographic laws. So the Big Bang becomes almost, the origin of time becomes almost, my laws, my equations just don't reach further backwards. What does that mean? It means some sort of epistemic horizon. Here we come to the beginning of what we can say.
But when you talk about quantum information, do you mean that matter is like an emergent phenomena from the quantum equations.
Exactly. Yep. Yeah.
Okay, so matter is not fundamental.
Matter, gravity, space-time. We are only seeing the tip of the iceberg of this, but what is happening in our field, in theoretical physics, is a very, very weird, fascinating connection between quantum information on the one hand and gravity, Einstein's theory, gravity, space, time, and so forth. It begs the vision, but no one knows how to make this concrete at this point. It invites the idea of thinking about the universe as some sort of quantum computer.
This is just fashionable now for a while, and then people will forget about it.
But last year's Nobel Prize in Physics was awarded to the quantum entanglement experiment.
Yes.
Do you think that quantum entanglement has a crucial role in?
Yeah, I think so.
Yeah.
In what way? Just shortly, could you say? I mean, the actual entanglement of two particles.
I think it encodes in a way we can hardly grasp at this point what time, what we perceive as time, what time truly is. You see, time has been the problem from the beginning in physics.
From the beginning. From the very first moment.
If we're going to truly understand the origin of time, we must eventually arrive at some sort of formulation of physics which doesn't rely on a prior notion of time, because that gets you into trouble with all your questions, right?
Yeah,
Before and this and that.
Okay, one last question, because we have to end. What is your answer, both of you, to the most fundamental question? Why does anything exist at all? I mean, instead of nothing.
I think it's. I can phrase my answer a little bit differently. I think it's absolutely essential to see the distinction between the real world and the mathematical models. And from my point of view, the real world is something that we have to take for granted. It exists out there, and we are trying to model it the best that we can. And I cannot see that we can do anything more than that. I think it's a confusion where you try to explain the origin of everything from a mathematical point of view. Then you are mixing reality with your models.
Thomas,
I agree.
You agree? Okay, but what's your own take? You get the last word now. Why does anything exist rather than nothing? In your words.
I completely agree with what Ulf said. So
that's good.
yes, it's the wrong, and it has to do with the point that has been recurrent tonight. We're trying to redesign, rethink, reimagine cosmology from within. We're trying to incorporate what Hannah Arendt would say in very abstract terms is our human condition here on Earth within this universe. We're trying to get this into the way we do physics. It's very different from the way physics has been done for the last 4 centuries, which was fine looking from the outside to some lab system or whatever. That's the big revolution, I think, which is going on, and I think on which we agree.
We actually do.
That is wonderful. Thomas Hertog, Ulf Danielsson. Thank you so much.
Yeah.
Thank you so much for coming. There will be book signing out there, both Ulf and Thomas. And don't forget to celebrate Isaac Newton's birthday on 25th of December. Thank you so much.